Yeah, okay. Good. Now we're recording. Lab 6, May 13, it's supposed to be due today, right? I can extend after the exam. Let's see, 13, the 20. Let's make do the 25 after the exam. Do we need an extension for lab 5 as well? See here, lab 6.
No.
You don't need? Okay. So let's put the 24. The exam is the 20th. Let's put the 22nd. And then save. More students coming in. Today is syllabus. Here let's go to the syllabus here. Today is Wednesday, the 13th of May. Okay, we'll be doing lab number 7. Lab number 7 is very similar to lab number 3. So if you understood lab number 4, very similar to lab number 4. If you understood lab number 4, you won't have any problems understanding lab number 3. And here goes special relativity. Let me fix that here. Relativity number, meter 3. That's okay. So exam is next week, next Wednesday. So get ready for next exam. Lab 2, okay, 3 and 4, right? I am going to watch out. Let me write that down in the notes. Chapters 22 through 26, labs 3 and 4, and notes right in here. Inserts. May 13, 26, Wednesday. Week 15, meeting 27. Week 15, meeting number 27. Another student trying to come in. And okay, watch 1. Watch for the correction of lab 4 the next couple of days. Okay, you have lab 1, 2, and 3 corrected, and you should watch for the correction of lab number 4 next couple of days. Let's emphasize the material for exam 3. Geometrical optics 2. for exam 3 so far? Exam 3. Okay, chapter 22. Chapter 23 plus that section of 20.5. Chapter 24, 25, and 26. Plus labs 3 and 4. That's what we have scheduled for exam next week. We will meet again on Monday, of course, and let's take a look at, yeah, we have to continue with relativity now. Am I recording? Yes, I'm recording now, right? Yeah, I'm recording. More students joining us. So last time we covered just the postulates of relativity. You have to memorize that. I'm gonna copy it. Did I do here? Okay. Last meeting, we covered the postulates of relativity, which are, the laws of physics are the same in every inertial referential frame, in every inertial frame of reference. Frame of reference. Okay, second postulate was a little bit difficult to swallow, not because of this formulation, but because of its consequence. And we're going to see the consequences right now. The speed of light postulate. The speed of light in a vacuum measured with respect to any inertial frame of reference will always be 300,000 kilometers per second, no matter how fast the source of light and the observer are moving relative to each other. And I illustrated that this postulate for you, right? Remember that for the rest of your life. It's rather difficult to swallow because we came from we covered material that contradicts this postulate. Is the covered material related to the relative velocity, relative position, relative velocity, relative acceleration. Let's get the illustrations here. Relativity, reflection, relativity, right here. And here you go. Second postulate, right? No matter whether the two referentials are at rest with respect to each other, they can be moving towards or away from each other, no matter what is the situation, what the situation is. The velocity of the light will always be measured as being 300,000 kilometers per second. And now we're going to look at the consequences of this postulate, of the second postulate. And I'm going to spell out first the consequences, and then I will prove them for you, okay? What are the consequences? What are the consequences of these two postulates, right? Okay, the first consequence, I'm going to spell that out to you, and I will be able to prove it, is that clocks that are moving relative to each other are seen to uh, to be slower, okay? Clocks that are moving relative to each other are seen to be, I seem to, let me get the student here first, okay? Are seen to be slower time-wise, okay? So that's what it means. That are moving relative to each other. Moving, the important here, moving relative to each other. That's the key, right? So if you have another clock, if you have a third clock, right? If you have a third clock next to the first one, comma, their timekeeping will be exactly the same. However, a second clock that is moving relative to the other two, will seem to be slower time-wise. What do we mean by slower time-wise, right? For instance, if the first and third clock times, right, 60 minutes, depending on the relative velocity of the second clock, it will indicate, let us say, 50 minutes instead. That's what I mean slower by slower. Time seems to flow slower. So it's just as though as you are looking at that, the occupants, right, of the second referential, and they're moving slower. That's one, not just they're moving slower, but they're aging slower. So it's not just a question of the time itself that's captured by the clock, but it's also the biological time of everybody else that is in that other referential. In other words, occupants of the second referential are seen to age slower compared to the occupants, to the observers of the first referential. This is a real life consequence of Einstein's first and second postulate. We can prove that. We can prove that. We are going to prove that. What else? Which other consequence do we have? Lengths. The lengths in the second referential the lengths, plural, are seen to be shorter as well. In other words, observers in the first referential when observers in the first referential measure the length of a given ruler in the second, not just ruler, but anything, right, that has a length in the second referential, they find the ruler to be shorter, okay? They find the ruler to be shorter. But it's not just the ruler, but everybody else that they see in there. Along the length shorter, along the length of travel of the vector velocity, along the length of the vector velocity of the referential 2. So those are two important consequences. There are more. See if I can get more here for you. Okay. Okay, he goes. Another one, two events separated by a time interval. Two events. Two events separated by a time interval delta t will be measured to be separated by a different time interval, delta t prime, time interval, delta t prime, in the second referential. So what do we mean by that, right? Suppose that two events separated by a time interval will be measured. Two events separated by a time interval will be measured separated by a different time interval in the second referential. So let me give you an example, right? As for instance, consider two lighthouses separated by a distance d in the first referential. These two lighthouses are synchronized with respect to each other. Okay. Now get two other lighthouses, and board them in the second referential, placed at the same distance d, according to an observer in referential 2. Observer in referential 2, okay? 2. The time interval measured by an observer in referential 2 still will be 0 seconds, because the two lighthouses are synchronized with respect to each other. With respect to each other, right? However, the observer in referential 1 will measure a time interval of delta t prime. Interval of delta t prime when measuring delta t prime. However, the observing referential will measure time interval delta t prime instead. Let's put it this way. Instead. Okay, another important consequence. Okay, when you measure the wavelengths of a light source, let's see. Say you are at rest with respect to a light source, a laser, for instance, a light source of wavelengths lambda. Wavelength lambda and frequency f. And frequency f. Say that you are at rest with respect to a light source of wavelength lambda and frequency f. When you measure the wavelengths, when someone else that is moving towards this light source, she measures a higher frequency and shorter wavelengths. Okay, that's what we call blue shift. Blue shift. Say that you're at rest with respect to a light source of wavelength lambda and frequency f. When someone else moving towards, when someone else is moving towards this light source, she measures a higher frequency and shorter wavelength for the same source. This is called the blue shift. Likewise, Likewise, if you are moving away from the light source, you measure a lower frequency, and a longer wavelengths for the same light source. This is called redshift. This is called redshift. Okay. 4 important consequences that scientists initially didn't believe at the time. There were even Nazi scientists that rejected completely the Einstein theory of relativity, not because the theory was incorrect, but because Einstein himself was a Jewish, okay? And that was very well documented in the literature. One of those Nazi scientists, what's his name, was a disciple of Heinrich Hertz. His name, let me see if I remember his name. It was Leonard, which was a scientist that worked in the same field that Einstein worked, who worked with what's the name? Oh gosh, even better, who was a famous Nazist scientist who rejected Einstein's theory. Was just Leonard, I forgot his last name. Philip Leonard. Okay, Philip Leonard. Leonard was his last name. Philip was his first name. Was the most famous and prominent Nazi scientist who vehemently rejected Einstein's theory of relativity. He was a Nobel Prize winning, and he won the Nobel Prize for the same theory that Einstein won. Okay, opposition to Einstein. Leonard rejected relativity as Jewish physics and a Jewish fraud, dismissing it due to both ideological anti-Semitism and his belief in a traditional ether theory. So Leonard himself believed in the traditional ether theory, which Einstein had rendered obsolete. Okay. Advocate for a job. Okay, along with fellow Nobel laureate Johann Stark, Leonard advocated for a German physics or Adian physics that focused solely on experimental results, rejecting the highly mathematical and theoretical work of Einstein. Initially, this Einstein theory of relativity was just theoretical work. Einstein's theory of relativity had not been verified experimentally, but Einstein lived long enough to witness a theoretical result that matched his predictions. Okay. Leonard was convinced National Socialist and served as was a convinced National Socialist and served as Adolf Hitler's court physicist and advisor. He published books that omitted all mention of Einstein and other Jewish scientists, despite their groundbreaking work. Okay, and what it doesn't say here, let's see, what was the work of Philip Leonard? Philip Leonard, let's see, Hungarian-German scientist. He worked on the photoelectric effect. Yeah, here you go. That's what his Nobel Prize was all about. And Einstein also was cited, when he won the Nobel Prize, was cited as for his contribution on the photoelectric effect. Okay. which was kind of hilarious, right? The same guy that criticized Einstein had this Nobel Prize delivered for the same, cited for the same contribution. Here you go, the photoelectric effect. So those are lessons that history teaches us, okay? Four different, like I said, four different consequences of Einstein postulates. And now, what the first one that you see right in here, okay, is referred to as time dilation. Clocks that are moving relative to each other seem to be slower time-wise. If you have a third clock next to the first one, their timekeeping will exactly be the same. Right? However, a second clock that's moving relative to the other two will seem to move slower time-wise, For instance, right? If the first and third clocks timed 60 minutes, depending on the relative velocity of the second clock, it will indicate, let's say, 50 minutes instead. That's what we call time dilation. This other effect here is, we call it length contraction. Second one here. Okay, and red, and here you go, we call the red and blue shift of the light, and which was exactly what Edwin Hubble measured for the first time for the galaxies that are very far away from the Earth. He discovered that the wavelengths of galaxies that are very far away was the wavelength was shifted towards lower frequency or longer wavelengths. Lower frequency, longer wavelengths. Okay. Oh, there are more. Let's see. Relativistic linear momentum. There is also Einstein's theory affects the linear momentum as well. Relativistic momentum must be here written to be conserved. Your regular momentum, P equal to mv, does not conserve from one inertial frame of reference to another. In special relativity, this relationship ends up becoming slightly different. Okay, we are going to talk about that. The relative velocities are also different, are also calculated differently. Okay, relative velocities are also calculated differently. Whereas Newtonian mechanics predict that relative velocity must be calculated either as a sum or subtraction, right? Of the velocities of the two referential, in relativity, this calculation is a little bit more complicated. Okay, example, if I'm moving at 50 kilometers per hour with respect to the freeway, right? In one direction, another car is moving 60 kilometers per hour towards me with respect to the freeway as well. Newtonian mechanics predict that the relative velocity would be 110 kilometers per hour. According to relativity, the relative speed would be less. And we can prove that. And what else here? One more important result that has applications in nuclear physics. And it was this very equation that predicts the atomic bomb, the energy of an atomic bomb. Objects have rest energy. That's called the relativistic energy, E equal to mc squared, the Einstein's most famous equation. This means that there is an equivalence between mass and energy, which in Newtonian mechanics, in Newtonian mechanics, okay, there is no such a, which in Newtonian mechanics, there is no such equivalence. There is no such equivalence. So 7 different consequences of the special relativity postulates, right? Plural. I'm going to prove the first one using the concept of the light clock. That's suppose that you can build a clock based on light. Okay, you have to imagine that. How does the light clock works? The light clock works like that. Here you go. Here we have a clock, and here we have a photon of light. Okay. As time goes by, let me put a different drawing here. So let's put that in our referential frame, right? I'm gonna put it here in the black referential frame. In the black frame of reference outline. Here you go. This clock here is in this is in the black frame of reference. Right in here. Okay. And referential A, referential B. Okay. Referential A is the black referential. Referential B is the red referential. Okay. Time of point P. Point P is the photon. Okay. Here you go. Here's the length. Let's put everything in black color here. So here you go. The here is my clock. You know, here you go. Look at my notation. Look at my notation, okay? It's the same notation that we used back in physics 6. Velocity of clock C with respect to referential A is 0, okay? This clock is at rest with respect to this referential A. As time goes by, and I'm going to remove any reference to referential B, okay? So you concentrate only on what I want you to concentrate. Light clock. This is our light clock. Let me erase here. C, light clock C. Light clock C. Time of point P with respect to referential A. That's it's gonna be here zero equal to 0. Why this thing doesn't? Let's see here what's going on. Okay, now so you start to get used to this notation. Okay, very important. Here go x-axis of referential A. I'm gonna make it a little bit thicker so it can look nicer. Okay, here you go. We made it. I'm gonna make it bold-faced here. Bold-faced, referential A. Instant of time 0. A little bit later on. So how does this light clock works, right? Think about two mirrors right in here, one at the top, the other one at the bottom. And what you see right in here is your photon. At time t equal to 0, the photon is moving towards the upper mirror, okay? So a little bit later on, this photon should be midway the distance between the two clocks. Okay, here you go. Okay, so here you go. 1, 2, 3, right? Every time that the photon reaches the mirror, it says a tick and a tock, right? Tick tock. Here you go. Here is half of the period of the clock. The photon is moving at the speed of the light. At the speed of the light. Okay, and go. I gotta get this one right in here. I gotta get this one right in here. I get this one right in here. And here's the final period. Okay, tick, tock, tick, right? And then everything repeats itself. Tick tock, tick tock. Play the movie. Tick, right? Tock. Tick, tock, right? Tick, and so on. That's how a light clock works. Okay? Do you have the picture now in your mind? How does it? Here's the observer. Okay, the big eye. The observer is represented by a big eye observing the clock and taking notes. Now, a light clock is a device that's made up of two mirrors facing each other and displaced by a distance d. Inside the light clock, we have a particle of light, a photon. This photon bounces back and forth. Bounces back and forth between the two mirrors. Okay? So before we get to referential B, the observer in referential A measures a period of what? The period should be what? Let's get the. Okay, that's what I want here. The distances between the two mirrors times 2, right? The speed of the light, right, of the photon would be the distance traveled by the distance traveled back and forth, right? Divided by the period of the clock. Make sense, right? And here you go, we can here write the period of the clock as being t equal to 2d over c. That's the period of the clock. This is the period of the light clock. Oops. Okay. Now the question that we ask is, what if we put the same clock in referential B that is moving with respect? Let's move with constant velocity, okay? With constant velocity with respect to referential A. And now we can use our other drawing. Referential B, observer of referential B. And now this clock, light clock, I'm gonna call it C prime, okay? Just to differentiate it from the previous clock. Here's the velocity of C prime with respect to referential B. It is at rest. However, the velocity of C prime with respect to A is going to be equal to the velocity of B with respect to A. Okay, this is a notation that we used in physics 6 when we were talking about relative motion, okay? Velocity of B with respect to A. Velocity of C prime with respect to B, right? And we can also say that the velocity of C prime with respect to A is equal to velocity of B with respect to A. Right here. Like that. So how do we calculate that? We use Einstein's second postulate, okay? So we are going to play a movie so you can understand how this light clock works, how we can use this light clock to find the phenomenon of time dilation. Okay, that's time t equal to 0. A time a little bit later, okay, the clock moved, right? From the left to the right. From the left to the right. See that? Referential B is moving with respect to referential A. And later on, further away, further away, further away, right? Further away. So this observing A is observing this clock. Not just observing this clock, but he also comparing this clock with the other clock that he has on board his own referential. Let's get that. That is his standard, right? So here you go. I don't want this guy here, but okay, we can leave it here. Send to the back. Send to the back, right? I want this one here. Let's see here. Size and position, format, shape. Let's see here. Fill. I want 100% transparent. Oh, didn't help, huh? Let's try it again. Transparent. What about this one? Transparent. What about this one? Oops. Transparent. Okay, good. I don't like that. They overlapped, right? I don't want those two to be overlapped. I'm gonna move it here to the. I'm going to take out this measurement here. Here is the clock C, light clock C prime, and light clock C. Those are two different clocks. Actually, they're exactly the same clocks. Okay, they're manufactured to specifications, so their specifications are exactly the same. It just happened that one stay in referential A, the other stay moving with referential B. Okay, so and the observer in A is using his clock as his own standard. He's comparing the measurement of his clock with the measurement of the other clock. There you go. Next. I'm going to move this clock a little bit to the right. Yeah. Right. This one moved a little bit upwards, but this one, because it's moving faster, right? This photon should be a little bit ahead of the other one. Bring to the front. In the next frame, right? Clock B moved a little bit more, and so on. So how can we derive an equation for the time dilation? All you have to do. That's what observer A see for clock B, right? Observer A see that clock B moved. The photon of clock B is moving in a diagonal line, right? So that's the distance that the photon has moved. It didn't see the photon moving a distance 2D. It sees a different distance. It sees a distance that is given by the right angle triangle, by the hypotenuse of this right angle triangle. This distance is D, right? And this distance here is the velocity times the period of the clock divided by 2. Velocity times the period of the clock divided by 2. If you square it and add to D square, you get this distance right in here. And take the square root, right? You gotta take the square root as well. Since the clock went up and down, you have to multiply it by this factor 2. That's what observer A sees. Okay, and the time, the period that observer A measures for clock C prime, right? Let me put C prime here. Instead of C, we gotta put C prime because the clock is moving. Is going to be given by this length that we calculated divided by the speed of the light. Whereas the time that the observer in referential B measures for clock C prime is 2D divided by C. Okay, so we're going to document that. This is the period of the light clock in a proper referential. And by proper referential means the referential in which the clock is measured to be at rest. Okay. Okay, so I'm going to use the notation here. The notation here is the period of the clock C prime with respect to referential B. C prime with respect to referential B. Oh, it doesn't like it, huh? C, D. Let's see. Now I can put the C prime here. Good. However, an observer in referential A measures a different period that I call T C with respect to A. And this period is going to be that one that you saw. This one right in here. Let me put TC prime. TC prime with respect to A is going to be the length that the photon travels as seen from an observing referential A divided by C. And this length that an observer in referential A times observes, right? This is longer than D squared. It's longer than D. Okay, and I'm going to emphasize here. Notice that this length is greater than D. Okay, so here we go. Greater than T C as measured by B. Don't forget C prime. That's how we prove mathematically the time dilation phenomenon. Here is the illustration, right? That you have to have. The red color means the clock that's moving. What else can we do? What time is that? Oh, we have a break, right? Let's take our break, and in this meantime, I'm going to update my computer. As you can see, I have to restart my computer. It's gonna take roughly 3 minutes. And let's see here. That is 10:46, right? So break 10:46 a.m. to 11:01 a.m. And stay here, don't log off, okay? That I'm going to update my computer, and once the computer is updated, I'll get back to you. Any questions before we go for the break? I see you in 15 minutes.